Started. Got it? Got it? Is the audio bouncing?
Yep.
All right. I'll begin with the word of prayer. Heavenly Father, we thank you for this day. Thank you for your students. Just pray you help us to use this time wisely. Try to answer any extra questions there might be. Remember, pray, Lord Jesus. Amen. All right. I had one request, so I'll start with that. Make sure I get to it. Let's see here. The request was to work problem 44 of chapter 3. All right, so that problem, here we're given h is equal to a in GL2R, so such that the determinant of a is a power of 2. All right. And we're asked to show that this is a subgroup of GL2R. All right, so let me first of all repackage this a little bit. What are we really saying? H is equal to A, 2 by 2 matrices, right? Over the reals, such that what? Such that the determinant of A is equal to 2 to the k, where, see, I don't know. I guess my immediate, the thing I don't know, does the term power include just positive powers or also negative powers? Well, I sure hope it includes negative powers, otherwise we're going to have trouble here. So let's say that k is an integer. I think if k is not an integer, if we just allowed positive powers, we'd quickly find the inverses that we need are not in here. Okay? So the only reasonable interpretation of power is that it's an integer power. All right? So to show that this is a subgroup, our goal, right? Show that H is a subgroup of GL2R. So what do I need to do? Step 1, notice that if we look at the determinant of the identity matrix, that's equal to 1, right? Which is equal to 2 to the 0. So therefore, I is an element of H. Now, just to be clear, we've had some sneaky problems about this in past exercises. Is that the identity for H? How do we know that? Well, we're looking to prove it's a subgroup of GL2, right? So it has to have the same identity if that's going to work. Right. In contrast, number 37 of chapter 2, we were not asked to show that G was a subgroup. It was just a group of 2 by 2 matrices. It was not a subgroup of GL2. But of course, you can easily verify that identity matrix has what? I times A is equal to A times I, right? Is equal to A for all A in R 2 by 2. So certainly it serves as an identity for anything. I don't think that needs to be said here, though, okay? I think that's clear. So what's next? 2, suppose that A and B are elements of H, right? Then what do we have? We know the determinant of A is equal to 2 to the k, and the determinant of B is equal to 2 to the L for what? For some k and L in the integers. That's what it means to assume that the elements are in H, right? Consider then A times B, right, has what? Determinant of AB equal to what? Product of the determinant product. So I can do determinant A, determinant B, right? So that's 2 to the k, 2 to the L, which is 2 to the k plus L. But hey, k plus L is an integer again, right? So that's an element of H, as k plus L is an element of Z. therefore what? Is closed under multiplication, right? Multiplication. I guess I'm doing the two-step test. Sorry. If I was more clever, I could have done one step. Oh well, it's too late. Suppose A is an element of H, right? Then the determinant of A is equal to 2 to the k for some k, right? Now, note 2 to the k, of course, is not equal to 0, so therefore A inverse exists. With what? With A times A inverse equals to I. What I don't know yet is that A inverse is also in H, right? I know that A inverse exists in GL2 from linear algebra, matrix theory, whatever you want to call it. And then what do I do? I want to show the inverse is in H, so I take the determinant, right, of this equation. And so this gives me that the determinant of A inverse times 2 to the, what was it, k, is equal to 1. So therefore, the determinant of A inverse is equal to 2 to the minus k, right? And of course, it's easy to see that minus k is an integer, right? The negative of any integer is again an integer. Excuse me. So what does that show? A inverse is an element of H. And we find H is a subgroup of GL2 R by two-step subgroup test. It's a very nice little homework problem, I think. Yeah. Okay, well that was the request, so now it's you guys. What do you guys want me to do?
I realize I should have come with a plan.
I mean, my question is there anything about this that you want me to talk more about, or does that make sense to you? Or let's see here. Yeah.
The one-step subgroup test or two-step subgroup test, that in why they can tell, like, those are subgroup.
So
That relation.
if we're given a group, right, in this case GL2, and we have something that's a subset of that, right? So the condition is you need a subset of a given group that's not empty, and then you can either use the one-step or two-step subgroup tests. If it satisfies closure for the two-step, if it satisfies closure under multiplication and closure under inversion, it then follows that the subset is also a group on its own right with the operations of the group restricted to it. If you didn't have this test, you'd have to take that object H and check all the axioms for a group. You'd have to check associativity, you'd have to check identity, you'd have to check inverse, you'd have to check closure. So this is a little bit of a simplification. We don't have to worry about associativity, right? And we don't actually have to worry about identity either. I usually look for identity because it's just something easy to find. All this does, showing this one, all this step really is for, I failed to say it, I usually almost always have said it up to this point, is that this is non-empty, right? So there's an earlier step here, which is, by the way, which I should say, H is a subset of GL2R. So like I need a subset that's non-empty, then I can either apply two-step or one-step.
Not empty set always identity. So
Not, well, if the identity element's in there, it can't be empty, right? But I could just as well show another matrix is in there to show it's not empty.
is it wrong if I say there is least one inverse?
At least one inverse. I'm not sure what you mean.
I mean, sometimes identity and inverse are the same.
No, the identity and inverse are not the same. No, 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 no. Identity element is, there's a unique identity in a group. We proved that the first day. And so it's that element that when you operate on other elements, it gives you back the element again. Inverse, on the other hand, there's a different inverse for different elements, typically.
But an identity is its own inverse.
That's true.
It's like the same.
Oh, yeah.
So, like, for example, in, let's say, U7, all right? So this is 1, 2, 3, 4, 5, 6, with multiplication done mod 7, right? The E, quote unquote, is 1. There's just that one. That is the only identity. That is the identity element. There are other quote unquote identities in the group. Like, we use the term identity as a word to express something that's true for all variable values. So you might find other quote unquote identities in that sense, but that is a different use of the word, unfortunately. For example, this is an identity. And that identity has nothing to do with this being the identity element. I mean, this is an identity, the Pythagorean identity, because it's true for all theta, right? That's a very different use of that word than saying that's the identity element. Inverses, right? Let's see here. What's we just fill out the Cayley table right quick. Here, I'll put a divider in at 3. I'll do the easy part. If I'm smart when I write the test, if I ask about a Cayley table, I'll just fill those in for myself and make you guys do this part. Less for me to grade, you know. 2 times 2, 4. 2 times 3, 6. 2 times 4, 8, which is 1. 2 times 5 is 10, is 3. 2 times 6 is 5. 3 times 5 is 15, which is 1. 3 times 6 is 18, which is 4. 4 times 6 is 24, which is 3. If we believe in the Latin square, 6, 5, 4, 3. Oh, there's 2 more choices here. Sorry, 5 times 6 is 30, which is 2. This has to be 1. If we do the group table right, every element should only appear once in each row and column. It's like Sudoku. What's Sudoku? So your 4 times 3 is 12, which is 5. I actually sort of know, I'm just being annoying. Let's see, your 4 times 5 is 20, which is what? 6.
And it says that number is going to invest with the
3 times 3 is 9, which is 2. Okay, anyway, enough. We can keep going here. But my point to you is you can see from this different things, right? For example, you can see that 2 inverse is equal to 4, right? And on the other hand, what do we have? 3 inverse is equal to 5. See, there's different inverses, right? What's 4 inverse equal to? 2? I guess I mean, these are kind of duals. Lots and lots of different inverses. I mean, different elements, different inverses usually. Yeah.
On the notes.
Oh, but the inverse is uniquely given for each element. That's another thing that's implicit within the first lecture. We proved that.
Trivial subgroup.
Trivial subgroup? What about it?
It has one identity.
Right. Yeah, so if you think about the set just containing E, of course that's a subset of G for any group, right? So if you think about this being H, well, H is non-empty, right? It's clearly a subgroup because the identity in the group is in the group, right? And if you think about the subgroups, the one-step or two-step subgroup tests, they're almost immediate, right? Like there's nothing to check because You can pick any A and B. Any A and B and H, well, that's just E. It's the product of E in itself. So pretty much the 1 and 2 step subgroup tests are immediately given to you by the fact that E times E is equal to E again. That shows that E inverse is equal to E, and it's closed under multiplication. So it's closed under inversion, closed under multiplication. So by the 2-step subgroup test, H is a subgroup. It's just a silly subgroup. Yeah.
Set is a subset of G, right? But obviously not a subgroup.
Right. Empty set cannot be a subgroup because it doesn't have an identity element. That is true. Yeah.
For a regular polygon, identity is a rotation by 0 degrees.
Mm-hmm.
Okay.
Right.
I mean, it sounded really intuitive, but I had to make sure I wasn't doing something.
Yeah, that's right. The identity is just a rotation by 0 degrees. So we could look at it that way. It's true. All right, let me see if I can find another problem for us to work in here. We could look at number 32. I'll look a little bit more at number 32 and where'd that go? I think chapter 2, number 32. So let's see here. We're in D4, all right? So the dihedral group of order 8, which is D4. We're supposed to simplify F R to the minus 2, F R to the 5, all right? And here R is the fundamental reflection of 360 divided by n degrees. And we're supposed to use a diagram to verify that F is equal to R inverse. Now, I showed you guys how that worked in class for, let's see here. Let me just kind of show you what's going on here. So for a square, right, what are the reflections that you can talk about for a square versus a triangle? Actually, these two kind of show you the difference. So if you look at these two different cases and think about reflections, there are different kinds of reflections for a square. There's like this one, right? Yeah, or this one, right? There's those two different kinds of reflections. Whereas for this one, the only kind of reflections are the ones that do like that. So every reflection for the triangle goes through a vertex. That's not a symmetry of the triangle. Because if you, thank you, yeah. True. Very true. And also, if we're doing that while we're at it, yeah. Okay, so he labels them H and V and D and D prime or something like that in the book, I forget.
Yeah, something like that.
So I basically showed you why that identity is true for this kind of vertex. Right? In class, we looked at like a 3-node thing, and we looked at how it's sorted through FRF. So the missing link in my argument would be looking at this sort of vertex, right? The other kind would look like this. And this would be the F, like that. So just number it however you want. Where do you want me to start with? 1 here, 2, 3. This would be N over here, right? So we can start with that because that's the other kind of vertex that can happen. I mean, if I could draw it worth anything, here's a 1, 2, 3, 4, 5, 6, 7, 8, an octagon, right? And so for the octagon, you also have like for the square, or you also have these guys through the vertices. You have those two kinds of reflections for an even-sided polygon. You have reflections either through vertex or through midpoints. There's both kinds of reflections. So to be completely, I mean, I proved this for the odd polygons, but not for the even polygons yet. So the proof for the even polygons, I'd start with this, right? Feed it. I want to prove that FRF is equal to R inverse. So first of all, let's do the flip. So the flip does, right? And what's that give us? What happens? N goes to, right? So we get 2, 1, 3, N, right? And then I do the rotation. And the rotation goes counterclockwise, one like that, one turn, right? So that does what? This is just a partial picture, right? You should imagine it going on and on, but
2, 1, and minus 1, starting there.
all right, very good. And then I should do another flip, right? Another reflection, if I believe the identity. I mean, hopefully, after we do this next flip, we see it's the same as just a clockwise rotation in R inverse, right? The inverse of a rotation is the rotation by the same angle, but in the opposite direction. So if R is clockwise, R inverse is counterclockwise is the way that works. Okay, so then let's see here. Flip, we get what? N, and then N minus 1 down here, and 1, and 2. Right? And yes, indeed, if you look at this, that's the same as starting from where we started and doing what?
1 clockwise.
Yeah, 1 clockwise. If we just go clockwise, then that gives us that.
Is there any particular reason that the rotation is automatically defined counterclockwise?
I don't know, why do we use counterclockwise angles in polar coordinates?
Okay.
It's a choice.
It's slightly mathematically consistent.
It's a choice. But you could replace R with R inverse everywhere and still have essentially the same, structure.
I guess it's just sometimes frustrating because you're taught to operate clockwise.
With clocks.
Yes, with clocks.
Yeah.
Now we don't use clocks anymore, apparently.
Maybe that's an argument. Well, then again, I say it's an argument against using clocks, but then you guys won't know what clockwise and counterclockwise means when we get to use the terms. So,
We'll go, what's a clock? It's a square box with some
so
numbers on it, right?
we need some sort of circular motion of reference in order to to define our rotational senses of orientation. I don't know.
So as
Yeah,
far
when the
as,
world moves all in the and how it's going to define that.
and then what's clockwise? Okay.
It'll be like references to some popular video game where something turns or something. I don't know. All right. So the point is, this is fundamental. And this is true for dn. All right? And also, the other thing that's true for dn is that f squared is the identity. Or 1 if you like. All right? Yeah, flip on flip, back where we started. So, excuse me. What this ends up meaning, all right, guys, is that any dihedral group can be rewritten as like the identity element, a rotation, a squared rotation, n minus 1th rotation, and then the the reflection times the rotation, and so forth, out to the reflection times the rotation to the n minus 1th power. And so that's why there are 2n things here. And so that's why that dihedral group has order 2n. So one of your homework problems is to find the Cayley table for, I think it was D3. Was that it? Or is it D4?
The next due homework has a problem on D5. I don't know about the other
Oh, yeah, thankfully I didn't ask you to find the Cayley table for D5.
That would have been kind of annoying.
That would have been mean. That would have been like 100 computations. Well, I guess less once you get used to it, but...
As long as you remember that it goes next.
But anyway, so here's just a sample calculation in D4. What we want, what he asks us to do is to take this, right?
Oh, you do have a Cayley table for D4, but it's not total maximum.
Right, that's not as bad. That's 64 things.
It's alright.
But really it's not, because the identity row and column, those don't really count, right?
Yeah.
So 64 minus 15 is...
Basically, it's some busy work to help us get easy points and drill into our heads that this is a thing that keeps working.
I almost agree with some of the things you just said. Let's see here. I don't think it's busy work, though. I think it's actually kind of important to do these things. Okay, so I want to take this, right? I'm going to rewrite this as R inverse, F, R, R to the fifth. I don't know. I guess I could write it R. I don't know if that's helpful or not. I better not do that. Let me just go back to this. So our goal, right, is to rewrite this in the form, either write this as, R to some power, or as F times R to some power. Okay? That's our instructions here. Oh, I'm sorry, he puts the F on the other side. He writes it like this. You could go either way. So I will try to follow instructions here and put the F on the other side. How do I do that then? So, yeah, this is true, but what else is true once you know this? Multiply by, we can also get from this F, R, F, F is equal to R inverse F, right? But FF is equal to 1, so we get FR is equal to R inverse F. That's super useful for these problems. So we can use that to manipulate. So like, I'm trying to move the F over there, right? So this is going to give me R, F, R inverse F, R to the fifth. I just commuted, putting the R to the other side changes it from inverse. And then that gives me R, F, oh, I'm sorry, I'm having a moment of stupidity. Then that becomes, right, R, RF, F, R to the fifth, right? So let's see, I switched the order of these two to start with. My next move was to use that, I'm going to have to make you guys be pretty explicit about what you're doing, otherwise it'll be impossible for me to give partial credit on these. Let's see, then when I got to here, I wanted to move the F over, and so I can switch the R inverse and the F. I have this identity here, but I also have, I can also take this and say F, F, R, F equals to F, R inverse, right? And this gives me yet another identity, which is that RF is equal to FR inverse. So that allows me to do what? Basically, I can switch the order of the reflection and the rotation, provided I change the rotation to the inverse rotation, or vice versa. See that? So again, taking this, multiplying on the right by F, on the left by F, gave me FFRF equals FR inverse, but FF is just the identity, so I get RF is equal to FR inverse. Now I can use that right here to change FR inverse to RF. And that's pretty awesome, because then I have RR, FF, R to the fifth. F is its own natural enemy. Those annihilate into nothingness, or the identity. And you have R to the fifth. And so what do we get? In other words, R to the seventh, and there it is. There's always going to either be one f or no f's left over after the simplification.
So r to the p, the answer is r to 7.
Yeah.
Is the only answer.
That is the only answer, right? Every one of these will simplify to one of the things in that list.
If
But this is in D4, can it be D7?
Oh, I'm in D4. I'm an idiot. I'm sorry. Yes, we can do better, can't we? R to the 4th is equal to what? What's that? Yeah, yeah. I mean, to be specific, there's a subgroup of D4, which is called what? You know, you have the rotation group, right? Rotation. So you could look at it like this, T of theta, such that what? T of theta functions from R2 to R2, such that what? How can I characterize rotations? Oh, I better be careful. You have a homework that's kind of picky about this, so I shouldn't dive into this just yet. Let me put the discussion of this off a little bit. But I don't know. I mean, basically, well, I don't want to rain on the parade of the homework I gave you guys, so let me stop here. But you could look at it as a group of matrices if you want. I mean, let me stay geometric for the moment. I'm sorry. So just what you said, r to the 4th is e. So this is really what? R3, right? There you go. Now, if this had been in anything larger than 7, it would be D7. I mean, be r to the 7th, right? If this had been a calculation in D8 or D9 or D10, whatever, there we couldn't have simplified, of course. But everything else stays the same. Ay, ay, ay. Let's see here. You guys have any other questions in particular? Let me work at number 30 here. Yeah. Actually, let me, number 30, well, no, I think I already did that one. Yeah.
it's okay.
Oh, 5:30. Yeah, I thought I started late. I was going to do one more example because I got started late. How about... I can't talk too long. How about number 9 in chapter 3? That one I can finish pretty fast. So here we're asked to show that U20 is not equal to K, the cyclic subgroup generated, it's not equal to the group generated by K for any K in U20. In other words, this means the group of units for Z20 is not cyclic. So we're talking about cyclic groups more Friday, but more systematically Friday. So what is U20? Yeah, 3, 7, 9. Not 18. I can't take 18 because 18 has 2 as a common factor. Yeah. So let's see here. Let's see here. What is... Let's see if I can show you this kind of a sneaky way. 9 times 9 is what? 81, which is 1 mod 20, right? So therefore, 9 is equal to 9 inverse, but more to the point, 9 squared is equal to 1. The order of 9 is 2. So that's out. How about 3? Well, 3 times 3 times 3 times 3 is equal to 9 times 9, right?
So the other half of 3 is 4.
Yeah, 3 to the 4 is 1. So the order of... So there's a theorem, which, by the way, says that the order of a subgroup is the order of the element. I don't know if I proved that yet. I have to do some soul searching about that, but it is true. And so, okay, well, that's 9 is out. And I mean, we need the order of the subgroup generated to be 8. Otherwise, it can't be 8. 1, 2, 3, 4, 5, 6, 7. Yeah, 8. How about 7? 7 times 7 is 14, right? No. Sad. 7 times 7 is equal to 49, which is 9. So that means that 7 times 7 times 7 times 7 is equal to 9 times 9. So therefore, 7 to the 4th is equal to 1. So the order of the subgroup generated by 7 is equal to 4. So that's not a cyclic generator for the group, right? So this is one way you can kind of knock options out by not, I mean, of course the boring and obvious solution is just to calculate the Cayley table and say, no, by direct, like just looking at everything. But these are some games we can play to avoid calculating absolutely everything. You know, how about 9? Well, we already ruled out 9. So we ruled out 3, ruled out 7, ruled out 9. How about 11? Well, 11 times 11 is 121, which is 1. So therefore, the order of 11, or the order of subgroup generated by 11 is 2. That's out. 13? Well, 13 times 13 is 169, which, by the way, is 9. So therefore, the order of the subgroup generated by 13, we've been down this road before. It's 4, by the same calculation as above. And
17 times 17 is 289.
And now here's how I'm going to do 17. 17 times 17 is minus 3 times minus 3, which is 9.
Because they're big numbers and you don't probably have it memorized.
Right, so like, I mean, I'd like to know 17 times 17 cold, but I just don't at the moment. I have a laptop. Cheating. But the point is, we're closer to 20 than we are to 0, so we might as well switch it to the negative. In this case, it helps us. Anyway, long story short, order of the subgroup generated by 17, 4.
I remember we did the same.
Yeah, 19 is very good. 19 times 19 is minus 1 times minus 1, which is 1. So the subgroup generated by 19 has order 2.
Which means that I don't think we've done
Right. If we were going to get U20 as a cyclic subgroup generated by one element, at least one of the elements would have to have order 8. And none of them do.
This is it.
Of course, the order of the identity element is 1. I didn't even bother with that one. So, therefore, U20 is not cyclic. So if we were going to have, if U20, right, was equal to the k, it would have to look like this. E, k, k squared, k cubed, k to the 4th, k to the 5th, k to the 6th, k to the 7th. We're about to prove this assertion, more or less. In the lectures that are upcoming, we're studying cyclic subgroups, and I'm going to prove some of these things I'm asserting at the moment. So in other words, to get back these, I need 8 things. The only way I can get 8 things is if I have an element of order 8, right? If this notation means that we're generating a set just from an element and its powers. So in order to have U20 a cyclic group generated by a particular thing k there, I would need at least some k which had order 8. But if you look at the different possibilities for k, 3, 7, 9, 11, 13, 17, and 19, all of them have order either 2 or 4. Or in the case of the identity 1, none has order 8 like we need. Therefore, U20 is not cyclic. There are probably other ways to argue this, but this is one way, looking at orders of elements. I might be putting the cart before the horse a little bit. It may be that some of the theory I'm using right now is actually in chapter 4. And maybe the purpose of this homework is actually to seed your intuition so that when you read chapter 4, it makes more sense. So, yeah. Anyway, we'll stop it here. I wish people would send in more requests. I don't know what to do when people don't send in requests. I was going to go pick out some today to have a game plan, and then I got roped into this paperwork debacle that wasted an hour of my morning. And
Your equivalent of like and subscribe and send in requests for more videos.
yes, please send in a request for more problems. Yes, us mathematicians, we're only happy if we have problems. It's not healthy, but it's true. All right, anyway, that's it.
Fascinating on problems, so I've never been happier.